Hello and welcome to 7.3 Part 2, continuing simplifying radicals using rational exponents. I think in the last video I said I might divide this into 3 parts. Nah. We're just going to do 2, okay? We're just going to cut it off here, and I'll talk about conjugates in class. That's fine, because this video is going to be jam-packed with lots of examples. So let's just dive right into it. Make sure you watch that last video, or at least have a solid understanding of the rules for exponents and radicals. That's all this stuff, and it was all talked about in part 1. But if you skip that video, well, if there's anything that's given you pause in this one, just go check out the other one, okay? Now, I'm not going to talk about these rules a lot because that's the whole point of the last video, but just so you can see, the 2 biggest rules we're going to use, at least in this video, are the rational exponents rule of rewriting it this way, right, a to the power of m over n. We say that that's the nth root of a to the power of m. And we'll also use this idea of negative exponents. And I do want you to notice that a to the negative n is 1 over a to the n. And consequently, if we had a negative exponent in a denominator, like so, I'd kind of like flip it up, right? So like, look, if you had 1 over x to the negative 2, that's equal to x squared, okay? Just kind of basic thing. Now, in here in blue, main idea. If you have variable, because what we're doing is simplifying radicals. And we've done simplifying radicals before, but we've just done them with numbers, right? Like, what's the square root of 125, right? 125. And I say, oh, well, that's root 25 times 5. And, of course, the square root of 25 is 5, so it's 5 root 5, right? Something like that. We'll still be doing that. There will still be numbers involved, but we're going to introduce the idea of doing this with variables now as well, okay? So essentially we are pulling out the variables the same way we might pull out perfect squares, right? Or it's kind of like looking like for that. And that's why we call this, we're going to use rational exponents to do this. Rational exponents being these 2 kinds of rules where we're writing them with rational numbers to help simplify. So jumping into example 1, all these are my favorites because they're so quick. Example 1 is going to use the first rule, that being the one right here. So this uses the rule where a to the m over n equals a nth root of a to the m. Or you can put the m on the outside of the radical or on the inside. It does not matter. In this case, we're given the cube root of x to the 12th, so I can rewrite that with rational exponents as x to the power of, well, m, being the exponent inside, is 12, and n is the index of the radical, which is 3. And now I do a quite simple division here. X to the power of 12 over 3, well, that's just x to the 4th. And hooray, we are done. So you see that is a rather quick example of rewriting that. Okay, so let's move on to example 2. And we're going to keep using this same exact rule, but it does there's one tricky rule, and that is what example 2 is supposed to illustrate, okay? The special case is when you simplify a radical with an even index. And remember, what I mean by even index is square root, 4th root, 6th root, and so on. Okay, the index is even. For odds, you don't have to worry about this rule. It's only even indices. Indices is the plural of index, by the way. So the first one is if your result has an even power. Now, when I say result, I mean after simplifying the radical, the power on the variable is even. So to do this, it's exactly like example 1. The square root of x to the 4th is, well, m is 4. And so this is x to the power of 4 divided by n, and n is a 2 because we're taking a square root. So I put a 2 here, okay? And I am going to erase that 2 right now. And so I say, well, x to the power of 4 over 2, that's x squared. and we are done. All right, finished. Look how easy that is, right? The special case is when your result has an odd power. Now, when you take the square root or fourth root or whatever, you're taking an even root of something, and then you have an odd power, we have to do something special. So I will write this kind of like we've been doing. This is x to the power of 2 over 2, which yields x to the power of 1. However, we cannot leave this as just x. The rule for when simplifying with an even index and you get an odd power, because the power in this case is 1, so it's odd, the rule is I must put absolute value bars around that variable. So I say absolute value bar x. Now you might be saying, why? Why do that? Why didn't we do that for the other one? And that reason is, well, you know when you take here, let me just look. What is 5 squared? It is 25. And what is negative 5 squared? It is also positive 25. So when I take a square root of, say, x squared, if x is negative 5, right? Look. So let's say x equals negative 5. Well, then negative 5 squared equals 25. But if I'm looking at the square root of x squared, then that'd be the square root of 25, and the square root of 25 is 5. It's not negative 5, right? This is because what the radical symbol indicates what's called the principal root. If you want to write that down, principal root, which means the positive root, positive solution. So whenever I take this square root of 25, I'm not going to get negative 5. However, negative 5 is a potential value for x. So this means that when I simplify this expression, I'm going to take the absolute value of it, because by taking that square root, I'm never going to get a negative result, right? That's essentially the idea. When you take a square root, the output is not going to be negative. Never. Now, we don't have to worry about this for odd indices, because when the index is odd, well, I can take the cube root of negative 125. It's negative 5. I can have negative outputs with odd roots. I just can't do it with even roots. And you might say, well, why don't we do absolute value x squared, right? Why don't I put the absolute values here if this is the case with even powers? And the reason is you don't need to, because whatever x is, it's getting squared, right? It's essentially already handling this issue with this absolute value. See, if it's square root of x to the fourth, well, let's say x is, I don't know, negative 2, right? So if x is negative 2, this is negative 2 to the power of 4, square rooted. And negative 2 to the power of 4, when you raise it to an even power, the result is positive. And so this is going to be the positive square root of, I think, 16. But of course, the root of 16 is 4. And my result of simplifying is x squared, right? So if x was negative 4, then x squared is negative 4 squared, right? And so I'm okay, essentially. Wait, is 2 to the power of 4 16? That is true. Okay. I don't know. I feel like I said something wrong there. I think I'm okay, but I don't want to slow the video down too much. But that's basically the idea, is because x is getting squared, that result's going to be positive either way. So I don't really care about the absolute value in that case. Okay? That's really it. That's why that rule exists. If you would like to talk about this rule more in class, well, we can talk about it. Okay? And so, yeah, just notice what I wrote here in yellow. you must have absolute value bars on this result, unless, of course, it specifies the variable is positive. If I just say assume x is positive, then I don't really have to worry about this. Okay? All right. Let's look at a combination of examples 1 and 2 here. So I've got the square root of 24 x to the power of 6, y to the power of 9. Now, the way I do these is just break it apart. I'm going to just say break it apart. And so we're just going to take this piece by piece. Let's say here's square root of 24. Well, square root of 24 is square root of 4 times 6, which that is square root 4 times square root 6. And of course, the square root of 4 is 2. So this is 2 root 6. So I know that this piece of the radical is going to simplify to 2 root 6. Now I'll analyze square root of x to the 6th. Well, using what we've just did, using rule number 1, which is up here in gold, right? That rule number 1 right there. The power is 6 and the index is 2 because it's a square root. So this is like saying x to the power of 6 over 2, which of course is x cubed. But hey, what did we just talk about? Special case, right? I've taken a square root. It's an even index, but the result has an odd power because the result is the power of 3. So I have to put absolute value bars on that x. Now we'll look at square root of 9, y to the power of 9, I mean. And this one's going to be a tad different. And this one might be a little bit more tricky. So to do this one, if you've noticed, you're really just looking at that exponent and dividing by 2, right? We could write this is equal to y to the power of 9 halves. But we want to simplify this. I'm not just going to rewrite it as 9 halves. I'm going to manipulate the powers so that I pull out those perfect squares that are within the variable. So here's how you're going to do that. 9 halves. Well, 9 halves is like how do you say? Y to the power of 8 halves plus 1 half. Is that true, right? Isn't 9 halves 8 halves plus 1 half, right? And I can do that, right? Now, because there's a rule of exponents that when you're adding the exponents like so, this is the same as multiplying the base with those exponents. Y to the 8 halves times y to the 1 half. And if you're not sure what that rule is, it's over here. Where is he? Oh, it's the first one right there, the product rule. And so that's what I'm using on this. So I've got my thing like so. And now, y to the 8 halves, well, 8 over 2, that divides evenly. So it's y to the power of 4. Now I have y to the power of 1 half. I can't simplify that anymore. So I'm going to change that back into square root y. And that is because y to the power of 1 half is square root y. Okay, and that's using that first gold rule at the top of this page again. Now, put this all together. Maybe I'll just put it back in blue. I'll say final result. Let's see, I've got 2 root 6. So I've got this guy, I've got this guy, and I've got this guy. So I'll say 2 absolute value x cubed, y to the power of 4. And now the things inside the radical, the things under the square root, are 6 and y. And so that is my final answer. This is a difficult example. I threw this on here because I wanted you to see a difficult example. Not all examples are going to encapsulate every single one of these rules like this, but I wanted to pick something, choose something, show you something that incorporates a ton of these rules all rolled into one problem. That way I'm not doing like 10 examples one by one. I can just kind of address these one at a time in one single problem. Okay, so that covers most of simplifying by radicals. The most important thing that's new being this absolute value business. You want to be really careful with that, all right? Now for some more problems. Example 4, 5, 6, and 7, and then that's it for the video. And these are just my examples. I actually don't have any practice problems for this piece of the video. We're going to get a lot of practice on this lesson in class, okay? You are welcome to try some of these for yourself, though. And maybe I might upload something to Schoology for external practice if you really want to. Okay, let's deal with some negative exponents here. So recall, on the other page, it says that x to the power of negative n equals 1 over x to the n. So essentially, if it's in the numerator, put it in the denominator. And if it's in the denominator, put it in the numerator, right? And then just get rid of that negative sign on the exponent. So this first example, example 4, really I find quite simple. We're going to rewrite this. Just if it has a negative exponent, just flip it. Just put it on top or put it on bottom. So notice I have x to the power of negative 3, right? That's going to go up top. So I will say x squared times x cubed. And then I've got times y to the power of 7, because that doesn't change. But then z to the power of negative 4, because that's on top and it has a negative exponent, that's going to come down. And so I'll say this is over, here's y to the power of 9 times z times z to the power of 4, because that got moved down. And at this point, just multiply, use your rules of multiplying the same bases and dividing the same bases, right? This is going to be x to the 2 plus 3 times y to the 7 minus 9. Notice because we're dividing, right? Y is 7 over y to the 9, which, by the way, you know that's going to be 1 over y squared, right? Because you're doing 7 minus 9. You're looking at the difference. There's 7 on top, there's 9 on bottom. 7 of those cancel out, and I got 2 y's on bottom. But I'm going to rewrite it just as y to the power of 7 minus 9. And then times 1 over z to the 1 plus 4. Okay? Yeah. There might be a way I could rephrase that, but I'm fine with that. So equals x to the 2 plus 3 is x to the 5. Then this is y to the negative 2. You know what? I'm going to do this. I don't really like that. I would rather write it with just negative exponents. This is z in the bottom, so it's z to the power of negative 1. And then this is z to the 4th, and that's also in the bottom, so I'm also going to do minus 4. Now this is z to the power of negative 5. And if I just flip these over one last time, x to the power of 5 will be on top, and y squared and ugly y squared and z to the power of 5 will be on the bottom. And now I will box that. A terrible box. I am going to take just a few seconds to try that again. Much better. Okay. If you have any questions on this, you just address it in class, all right? And write your questions down. If you got questions during this video, write it down in your journal. It's wonderful practice. Wonderful practice to do that. Okay. Example 5 and 6 are really quite fast. Example 5, rewrite the expression as a radical. So really just practice manipulating, going back and forth, the flowing between rational exponents and radical expressions. So when I say t to the power of 3 halves to the power of negative 1, well, that is, there's actually a few ways you could write this. And that's the joy of manipulating exponents, is there's a lot of ways you can approach these depending on how you like. First approach, you could say that, oh, this is t to the power of 3 halves times negative 1, in which case this is t to the power of negative 3 halves, right? And if you do that, then you know that this equals 1 over t to 3 halves. And then you can convert your t to the 3 halves. So I'm actually, you know what, I'm going to erase that so it looks nice and pretty, because I actually do like this approach. Here it is again, a little bit slower. T to the power of 3 over 2 to the power of negative 1. That's t to the power of 3 halves times negative 1. There's a rule for that, for raising a power to a power. That rule is on this first page. It is called the power rule. Okay? And I'm kind of using it in reverse. And now I'm multiplying 3 halves and negative 1, which is just negative 3 halves. And now, by using the rule of negative exponents, it's in the numerator, so I'm just going to do 1 over t to the 3 halves. And now that I have that, kind of no more negative exponent, right? I can say that this is, m is 3 and n is 2, so the exponent's 3 and the root, or index, is 2. So this is actually 1 over square root t cubed. And that's using that first rule, number 1 in gold on the previous page. There you go. You've rewritten it as a radical expression. Technically, this isn't simplified, but that's fine. It's okay. That's how it wanted us to write it. It's just a radical. Yeah. Okay. I'm just saying this because you could probably simplify it like this. But I'm not going to talk about that right now, okay? It's fine. It's fine. Example 6, rewrite the expression using rational exponents. So we're just going to kind of do the same thing again, but just the other way, right? It's kind of like starting with what I boxed and going backwards. Okay. So on the top, I have an index of 2 and a power of 5. So this is x to the power of 5 halves. This is square root. Divided by cube root of x to the 7th, that is x to the power of 7 thirds. And since I am dividing these fellas, right, it's x to the 5 halves divided by x to the 7 thirds, I will subtract their exponents, 5 halves minus 7 thirds. Now, I have to do that, right? What is 5 halves minus 7 thirds? Well, let's get a common denominator, right? X to the power of, multiply it by 3 over 3, so it's 15 over 6, minus times 2 over 2, that's 14 over 6, which equals x power of 1/6. Let me be consistent with the way I write my fractions. 1 over 6. And now that I have, it's x to the 1 over 6, hey, that's about as simple as that fraction's ever going to get. And I want to rewrite it. I guess we're done. Sorry, it said using rational exponents. So there you go. Okay, yeah, we're done. I was going to say we could rewrite this now as the 6th root of x, which is true. But I guess this question just asked to rewrite it with rational exponents. Okay, cool. That's fine. We can erase that, and we will box this answer. X to the power of 1/6. Oh, rewrite it. Come on, Mr. Spank. 1 over 6. I know it doesn't matter. I just want to be consistent. Okay, one more example, and then we are finished with this. And this is example 7, simplifying something that is just plain hideous. So I made this as just a bunch of stuff. okay? The way I would deal with this is just break up like each like term. Notice what's in square roots, right? We do have a rule. You can check it on that rule page. There is a rule that the square root of a over b is equal to the square root of, is equal to the square root of a over the square root of b. So see how, like right here, I've got root 10 and root 5. Now look, there's a bunch of junk attached to it all, but I can also separate radicals using multiplication, right? Like, what I mean is like 10 x cubed, you can separate that as root 10 and root x cubed, right? We're allowed to do that. The same way we're allowed to separate or combine division. So what I'm going to do is sort of pair every term if it has one on top and bottom. So let me just write it and maybe you'll see what I mean. Root 10 and root 5. That's square root of 10 over 5 times, I've got x cubed in the top radical and I've got x in the bottom radical. And they both are square root, so I'll do square root x cubed over x times, I have y to the power of 8, but there is no y in the bottom, so I'm just going to leave that as square root y to the 8th times, now I've got z in the bottom, but no z in the top, so I'll just do like 1 over root z to the 10. Okay? And we'll just take this piece by piece. 10 over 5 is 2, so this is root 2 times root, this is x cubed over x, that's x squared, times this other business, right? Y to the power of 8, and yeah. So let's use those rational exponents now. This will be y to the power of 8 halves. And we know this, right? Because we're just using that first golden rule. We just use it so much, right? And when I say golden rule, I'm talking about this one. We're using this rule constantly, and you gotta know this by heart. You gotta burn it into your brain, that rule, and you gotta be able to recognize it and use it fluidly. Okay, so it's y to the power of 8 over 2 times 1 over z to the power of 10 over 2. Okay, and so when I simplify all this, I've got root 2, square root of x squared is x. But hey, you're taking an even root and the result is an odd power. That's absolute value. Then again, y to the power of 8 over 2 is y to the 4th. I don't need absolute value because the result has a positive exponent. And now it's 1 over z to the power of 5, because 10 over 2 is 5. And hey, that's a square root, and the power is odd, so that's also absolute value. Putting all this together, final result, you should have absolute value x, y to the power of 4, square root 2, over absolute value z to the power of 5. And we shall box that and call it a day. And that pretty much ends this video. Now, I will say, I don't think this example 7 with just ugly hideousness, I don't think there's anything on our quiz or test that's going to give you that much thinking. We will probably assess you on each individual one of these skills, or maybe a couple of them in one. I'm not going to throw you all of this at once, but this is how you. I wanted to show you an example where It really is ugly, and you just got to break it down piece by piece till you got it. Okay, that wraps up this video. I know it was a lot of examples, and I know that this video was probably long, and I know that the last one was kind of like 30 minutes, so I am sorry, but I hope you were able to watch this before coming to class with no issues. Okay? If you think it was too long, you think you weren't able to do this, let me know. Okay? And I'll try to be a little bit quicker in the future. But thanks for watching. Thanks for being here, and I'll see you in class.